Swayam Prabha. Digital India. Educated India.
So what I'm going to do is, again I'm going to give a little bit of steering to where our course is going. Okay, I'm going to say certain things, and that will be the motivation to what we are going to do next. Okay, so of course I can directly embark on doing something that's very technical. Okay, but then it doesn't I mean, it's not appealing unless you see that there is a motivation for that. Okay, so to begin with, what I'll do is, let us recall this business of the so-called signed normal and signed curvature. Okay, look at that idea. So so here so let me write this idea, the idea of signed normal and signed curvature. So you see, this idea of signed normal and signed curvature, we arrived at them from a kind of geometric point of view. Okay, so what was the let me remind you how this was done. So basically we took a picture of we took a picture of a curve given by gamma of t. Okay, then so gamma of t is a parameterization. All right, then what we did is we took a point on the curve, let us say so it's given by gamma t naught, which is a point p naught. All right, and at that point, what we did was we found the best fitting circle, which is a circle of curvature. Okay, and so we have this you have a picture like this. There is a best fitting circle at that point. So in this case, probably it should be kind of like this, and the center is somewhere here. So you have, this is the circle of curvature, or rather a part of it, because I have to draw a very large circle, because the portion where I have drawn it is kind of more or less curved. Okay, so it will be a circle with a large radius, and of course the radius of curvature is the reciprocal of that. Okay, so you see the curvature will be very small. Okay, the larger the radius of the circle of curvature, the smaller the curvature. So this is the circle of curvature at p naught, so it is c p naught. Okay, then this, you have this c sub p naught, which is center of curvature. Okay, and incidentally there is this other term for circle of curvature, which is called osculating circle. Okay, and the literal meaning of osculating circle is a kissing circle. Okay, that is, it's a circle that is kind of as close to the curve, it's the best fitting circle to the curve. Okay, so there is also this this terminology, osculating circle. Okay, so now anyway, see, what we did was we wanted to write down a vector. See, we wanted to get a formula for the center of curvature, and if you recall, we know that at this point p naught there is a tangent vector given by gamma dot of t naught, that is a tangent vector, and then you know that you have to take the normal line. Okay, you have to take the normal line to that, and this center of curvature will lie on that normal line, you know that. And how did you arrive at the center of curvature was by taking a nearby point, drawing a nearby normal like this. So let me draw this a little better. So here is a normal line. So this is the normal line at p naught. Okay, and then how did we get this point? We got this point by taking a nearby point, which is gamma of t naught plus delta t, and then you drew the normal there at that point. Okay, and so you'd be so let me draw it like this. Okay, And of course, at that point, you will have a tangent direction, which is gamma dot of T naught plus delta T, right? And these two, normals, they meet at a point. And so this point was C sub delta T. Okay, and see, this point depended on delta T. As delta T goes to 0, you see this nearby point, let us say P, which is P of delta T, basically it's a function of delta T. That P approaches P naught. Okay, then these two, the intersection point of these two normals goes and hits the center of curvature. Of course, it could have gone to infinity, because after all, both normals are becoming the same, and you might have imagined that it might go away, but it doesn't. It actually goes to a finite point, and that is the center of curvature. We got this formula geometrically by applying just simple plane analytic geometry and calculus. Okay, and of course, this normal is normal at T naught plus delta T. Okay, but anyway, the point I want to say is that when we tried to write this down as a vector equation, there was the necessity to introduce this business of sine normal and sine curvature. Okay, so I am trying to tell you that the idea of sine normal and sine curvature, okay, this was necessitated in a geometric way. All right, so what was that? So what you do is that you take this, put the origin here. So you think of so you think of this point P naught as also position vector gamma T naught. Okay, now gamma T naught is also thought of as position vector. So we have always this duality. You take a point in space, either you write the point as coordinates, or you also think of the point as position vector of that point with respect to the origin. So this is a dual notion that we always keep using. So this is a vector, and you see, I wanted the vector for the position vector of the center of curvature. So that would be this vector. That would be this vector, and this vector. So that was before taking the limit. Oops. Let me get rid of that. So I want the other one. So I have to join it to Cp naught, not to C delta T. So get rid of this. So I have to join it to this. It's somewhat messy. Okay. Okay. So let me make it a little bit better. Oh no. So this guy is C delta T. Okay. So let me write as delta T goes to 0, C delta T goes to Cp naught. Okay. So yeah, so I'm interested in this vector O Cp naught. Okay, so this vector, I call it as epsilon of T naught, and it is the position vector of the center of curvature. And I told you the locus of the center of curvature is called the evolute of the curve, and that's why I use epsilon for this vector. And by vector addition, you know that this epsilon T naught vector, and I will suppress the arrow. Okay, so epsilon T naught vector is gamma T naught vector plus this. You see this normal vector here, normal to the curve. Okay, so this vector, you see, if you call it as n hat, okay, at P naught, then you have a very simple vector equation. You have epsilon of T naught is equal to gamma of T naught plus n hat P naught. You have this times this length. Okay, the length is from P naught to Cp naught, and that's the radius of curvature. So I should write into a radius of curvature at P naught. Okay, or of course this can also be written as radius of curvature at T naught. Okay, so this was the vector equation. All right. Now what is the problem with this geometric diagram? The problem with this geometric diagram is that I have put I have taken a unit vector, normal vector, which is pointing towards the center of curvature. Okay, mind you, I could have, in principle, I have tangent line, and I also have a well-defined tangent vector, which is gamma dot. That comes just from the parameterization. But when it comes to a normal vector, there are two choices. I only have a normal line, and I have two opposing choices in two opposite directions for the normal vector, and there is an ambiguity. I have to choose it correctly. So what we did is we did the following geometric thing to make this, because this n hat P naught is geometrically defined. It is the unit vector from the point on the curve pointing towards the center of curvature. And you see that changes, that will change depend on whether the curve is concave or convex, okay. So that's not, I mean, it's geometrically defined and it's not analytically defined, okay. So you see, there is this, throughout this course, what is going to happen is that you're going to have something geometric that you arrive at in a geometric way. Then you, just to fix the geometry, you make some definitions. Then the next question is, now come on, forget all the geometry. Purely using mathematics and analysis, analytical techniques, you describe the same thing. So, you know, without pictures, whatever, if what you're saying is correct, even without pictures, you should be able to write a formula, you should be able to define it correctly. See, for example, this is the way we got the formula for the curvature, okay. What is the geometric formula for the curvature? We got, you see, we got gamma dot, curvature at t, for that matter at t, curvature at t is, we got this formula, which is, you know, a norm of gamma dot cross gamma double dot by norm gamma dot cube. We got this formula for the curvature. See, we got this formula geometrically, but then, you know, at that point of time, you know, everything was geometrically defined. The center of curvature was defined as the center, of the circle of curvature. The circle of curvature was defined as the best fitting circle. So everything was kind of geometric, okay. And the only analytic thing we used is we used gamma t, which is one parameterization of the curve and which is kind of regular in the sense that gamma t should never vanish. I mean, its derivative should never, gamma dot should never vanish, okay. But then what did we do? We did this business of trying to redefine curvature analytically and then use proper vector calculus to get the same formula. And it turned out that what we proved in the last few lectures is that this formula works even for a space curve. So you see, there is this translation, and of course, you know, this involves some work. What you had to do is, you had to say that, you know, if you want to define curvature, scalar curvature of a curve, then you have to do the following thing. First, you know, you make it as units, take it to be unit speed, parameterized. Then you measure its acceleration vector, then take its magnitude. That's your curvature. Then this bought into this business. Why do you want unit speed? And that had physical reasons that had to be justified, that could explain it. Then you also needed to have this result that you will always get a unit speed parameterization for any regular curve, okay. Unit speed means that, you know, the speed is constant, non-zero, it's equal to 1. That means in particular it has, the tangent vector can never vanish. That means velocity vector cannot vanish, so it is regular. But conversely, if you take a regular curve, does it have unit speed parameterization? That was the question. And then we said, yes, it is just because of arc length. Arc length is the correct parameterization. We proved all this technically, all right, completely mathematically. And then after doing all that, you know, you got the same formula working for even for a space curve without using any geometry. That's what you have to appreciate. So you see, there is this translation starting with something geometric, and then you are slowly bringing it down to completely the analytic side. See, this is the translation from geometry to mathematics, okay. Mathematics is inspired by geometry, but at the end of it, you need to define everything accurately and you need formulas for that which agree with what you geometrically got first, okay. So in the same, see, this the same game we are attempting now with this idea of signed curvature, okay, and signed normal. So the signed curvature and signed normal was designed or defined so that you are able to write this equation all the time, okay. So the only problem is that geometrically, when you write this n hat p naught, it is the unit normal from the point towards the center of curvature. But I don't know where the center of curvature is. I mean, this is just a geometric definition. But how will you write it analytically? So if you want to do something analytically, it should be based on something that is already well defined. So what is well defined in this case? It is a tangent vector. Once you give me the parameterization of gamma t, then at that point gamma dot t is the tangent vector, and that is well defined. It is a vector, so it's well defined. The direction is well defined. Now what I did is, based on that, I wanted to define for sure, and that's how I got the sign normal. So what I did is, I took the tangent direction, rotated it by 90 degrees anti-clockwise, and said we fix this as the sign normal. Okay, so it was a geometric definition. So ns hat is equal to so I'll write it as ns hat if you want at p naught, let me put p naught. Ns hat at p naught is the signed normal at p naught and this is just, you, yes, and of course I want to say sine unit normal, okay. And this is, how is this? You take the tangent, take the unit tangent vector, rotate it by 90 degrees anticlockwise. So this is rotate the unit tangent vector. And what is unit tangent vector? Gamma dot p naught is the gamma dot at p naught, or you can write as gamma dot of t naught. That is the unit. That is the tangent vector. You divide it by its length by norm gamma dot of p naught. This is the unit. This is the unit tangent vector. This is unit tangent vector. You rotate this 90 degrees anticlockwise. Okay, by 90 degrees in the anticlockwise direction. So this is the definition of the signed unit normal. Now the problem with this definition of the signed unit normal is, because of the way in which the curve is traversed and because of the way the tangent is pointing out, it may happen that the signed unit normal may not point towards the center of curvature, it may point away from the center of curvature. Therefore, what you do is, if I want to replace this geometric normal, which is pointing, unit normal, which is pointing towards the center of curvature, the signed unit normal, I have to tinker with this R term. Okay, because there is, for all you know, the geometric normal and the signed unit normal may be in opposite directions. So you see, there I told you that there are four possibilities. If the curve is going like this, okay, and your tangent, your gamma dot is like this, okay, then in this case, the circle of curvature is on this side, so this is the center of curvature, and in this case what happens is that this is the unit normal at p naught, okay, and if you rotate the unit tangent vector in the anticlockwise sense, you will again get the signed unit normal. So here there is no problem, but you just reverse the orientation, you will be in trouble. So instead of going like this, suppose I went like this, then what happens is, at the same point, you see the tangent vector will now become like this, okay. Now again, the circle of curvature has not changed, the center of curvature has not changed. Now the geometric normal will be, so the geometric normal will be like this again. So this will be your n p naught hat. So this point is p naught if you want, okay. And what is a signed unit normal? I have to rotate the unit tangent 90 degrees, so it will come the other side. You will get it like this. You will get the ns hat p naught will be the other side. And you see that this is now minus of n p naught hat. So you see, the problem is that when you define the signed unit normal, it may go opposite to the geometric normal. So in that case, if you want to replace this geometric unit normal by the signed unit normal, a sign will come in, and that sign has to be adjusted. How do you adjust the sign? You cannot, of course, I have to put the sign, I have to put a minus sign to the radius of curvature. But that's nonsense. I mean, radius of curvature is supposed to be always positive. So the trick is, you put the minus sign to the reciprocal of the radius of curvature, which is the curvature. So you call the curvature as negative and put the blame on the curvature. You put the negative sign to this curvature, okay. That's the trick that you do, and call the curvature a signed curvature. So what is happening is that, the sign is absorbed into the curvature. You are not messing with the radius of curvature, okay. So what happens is that, with this whole equation can be written in a nice way, and if you write it in this way, you now have an analytic expression where signed unit normal is defined in a concrete way, and I am not using the geometric normal. You understand? So I will get epsilon of t naught is equal to gamma of t naught plus I write signed unit normal at t naught times, I will put 1 by ks at t naught. So this is the big deal. This is the signed curvature at t naught. Okay. So you see, what has happened is that in this geometric expression, where I have, geometric normal and the radius of curvature, I have tinkered with it and made it into a expression that will work for all cases where this is analytic signed unit normal. It's analytic because I got it from the gamma dot by rotating it by 90 degrees, and it's kind of completely mathematically defined, okay, not geometrically defined. Okay, rotating a vector by 90 degrees anticlockwise is a mathematical operation, all right, and in the sense that it can be written down and analytically mathematically. Rotation of a vector can be written out, for example, in linear algebra using a rotation matrix if you want, right? So this is like analytically defined, and you see I have cleverly absorbed the sign into the curvature, and this Ks is going to be minus 1 by r t naught or plus r 1 by r t naught, depending on whether this this signed unit normal is pointing in the direction of the geometric normal or away from it. If it's pointing the other direction, you get a minus sign. That minus sign I am absorbing in the curvature. And so now comes the big deal. So you see, this as it stands, this seems to be only a game of adjustment. You are only you are adjusting the sign of the curvature so that you are able to write this expression all the time. All right. Now the question is, again we have this question. Whenever you do something geometric, try to make it completely analytic. Okay. So the question is, after you do this adjustment, what is the meaning of the sign to the curvature? So you have to ask this question. What is the sign curvature? How is it? I mean, give me something about it analytically. Okay. Geometrically, you understand sign curvature is negative if you see the sign normal is away from the pointing opposite to direction to the the geometric normal, and it is positive if the signed unit normal is pointing towards in the same direction as the geometric normal. What is the other way to say it? The sign curvature is negative if the signed unit normal is pointing away from the center of curvature, and it's positive if the signed unit normal is pointing towards the center of curvature. All right, but this is all geometric, you see, pointing towards, pointing away from. How will you give it an analytic meaning? So that is a question. So you see, this is always going to happen throughout this course, and for that matter, anything you take in geometry or in real life, you translate it to mathematics, you slowly start making everything analytic. And unless you reach the final stage where everything is analytic and you can write everything purely mathematically without a picture, then you have not completely made the translation to mathematics. So the question that this raises is that what is the analytic meaning of the sign curvature? What is the meaning of putting that sign? It looks like you are just putting plus minus, okay, to adjust this. But what does it mean? So there is a nice meaning to that. And not only that, that meaning, trying to understand that meaning, gives rise to several amazing results. Okay, one of them is the Hopf Umlaufsatz, which is the simplest version of the so-called Gauss-Bonnet theorem. All right. The other thing is trying to describe the dynamics of a moving particle by a matrix differential equation, okay, which is given by in terms of what is called the Frone-Serre frame. It's called a moving frame. Okay. So all these things, okay, if you clarify this business of what this sign curvature is analytically, all these questions are answered. Okay. For example, you can even prove these kind of statements. We have seen that if you have a straight line, then the curvature is 0. All right. If you take a circle, the curvature is positive constant. All right. Now you can ask this question. Suppose I have a curve for which the curvature is 0. Okay. Is it a straight line? It should be. Okay. Geometrically, it's evident. Prove it analytically. So this is, you see, this is a mathematical challenge. Right. Now you can write a proof for that if you understand this question. Similarly, suppose I have a curve. If you take a circle, the curvature is a positive constant. It is just the reciprocal of the radius of the circle. Conversely, suppose I give you a curve. Suppose the curvature is a positive constant. Can you prove that curve is a circle? Geometrically, it will look intuitively correct. But can you write an analytical proof? The key is in trying to understand the sign of the curvature. Okay. So you see, so I'll write this question. So the question is, give an analytic expression for or related to the signed curvature. Okay, and this question is what we want to answer next. Okay, and it is going to help you to answer many other things. So what are the applications of this question? The applications of answering this question, I will tell you something about that. And these are what are the topics that are going to occupy us in the next few lectures. Okay, so the first thing is, you know, the so-called Frone-Serre frames. Okay, so let me write it correctly. Oops. So I'll tell you what this is all about. So you see, suppose for the moment, you know, this works for plane curves and space curves, but I'm just doing it for plane curves. So you see, suppose you are moving on a curve. Okay, see, people who do physics, they study this thing called frame of reference. Okay, what is a frame of reference? See, what you do is basically it's a coordinate system. So for example, if I you suppose you want to you know, quantify all the points in space with coordinates, what you have to do is you have to choose a point, then you have to choose the three axes. That means you have to choose three mutually orthogonal unit vectors. It's an orthonormal set of vectors. Okay, and usually you choose ijk and you use a right-handed system. Okay, which is what we do. Okay, and this choosing this ijk, what does it do? It gives for every point x, y, z coordinates, or that position vector of the point is written as xi plus yj plus zk, where ijk are the three unit vectors in three x, y, z directions. Okay, that's what we normally do. So this frame of reference has got to do with choosing this, you know, set of unit orthonormal vectors. That is what is called a frame. Okay, and it's called a frame of reference. So if I fix a point here somewhere and take three directions, three mutually orthogonal directions, and take three unit vectors, then I am actually fixing a frame of reference. Okay, and in physics what happens is that if you start moving, then you and you know, either you can be you can be at one point and look at an object moving, then you are the point of reference and you have a fixed frame of reference. Okay, on the other hand, what you could do is you might be the fellow traveling. Suppose I am moving on a curve. Okay, then I know as far as I am concerned, I have if I can fix three directions for me at every point on the curve which are mutually orthogonal, then what I have done is I have fixed a frame, and the point is this is what is called a moving frame. Okay, so there are fixed frames of reference, there are moving frames of reference, and you can understand that the movement of the frame encapsulates the movement of the curve itself. Okay, so what does it mean? See, for example, if you have a 2D curve, okay, and suppose you write it as gamma t, then at every point there is a very nice frame. There is this t dot, there is this gamma dot, which is the tangent direction. Okay, then there is a sign, and you know, I can, if you want, I can take the t cap vector, which is notations. So let me do the following thing. So we will use t cap at t, which is the unit vector, which is going to be, you know, gamma dot t by norm gamma dot t. This is one unit vector. Then the other unit vector will be the sine normal. So I can take this one. Okay, I am putting this cap just to tell you that it is a unit vector. And you see, these two are orthogonal. And you see, this is a moving frame now, because it changes with t. At this point, I have taken these two. If I go to some other point, then you know, I'll get you know, the other way around. So I'll get another set like this. Okay, so if this is some t1, I'll get at this point I will get, so let me write the two fellows. So this will be T cap at T1, and this is P naught, this is gamma T naught, and this is, let us say, P1, this is gamma of T1, okay, and this is 90 degrees, and you are going to get, this is ns hat at T1. So do you see that at every point there is a frame. So you get this T and N, T and Ns, T cap and Ns cap, and this is a moving frame, all right. And the point is that somehow, you know, as you move along this curve, this frame is also moving, all right. And somehow the way this frame moves should give you the curve. If you can keep track of this T cap and this N cap, okay, that should tell you how the curve is curved. That should give you the whole curve, basically, right? Now, you see, we want to make this statement from this very geometric statement, you want to make it analytic, okay? So what happens is that this, you know, can be written down, okay, as equations of motion. So actually, what happens is that as you are moving along the curve, there is this frame, but you see, you can also differentiate this frame. See, because the movement is controlled by the velocity, okay, if I want to keep track of the curvature, okay, which is essentially the curve, if you want to keep track of the curvature, I have to differentiate the unit tangent vector. And remember, if you differentiate the unit tangent vector, you will get the, basically you should get the curvature, okay. If you for example take the curve to be arc length parameterized, then it is already unit speed. The tangent vector is already a unit tangent vector, okay, and differentiating that will give you the second derivative, and that's the acceleration vector. Its magnitude is the curvature. So you see, what is happening is that if the curve is controlled by, you know, this T cap, this ns cap, and their derivatives, T cap dot, ns cap dot. It is controlled by these four things. This T cap dot is going to give you, you know, a measure of the acceleration, because T cap, if you take unit speed parameterization, T cap is the same as T, and T dot is the acceleration. T is already the velocity. T dot is acceleration. Its magnitude is the magnitude of the acceleration, which is the curvature. Okay, so you see, the curve is controlled by this, literally. Okay, and basically, what are you saying? See, think of a curve for which at every point I am giving you a frame. Not only that, I am telling you how this frame is changing. How do I say how the frame is changing? I need the rate of change of the frame vectors. What are the frame vectors? The T cap and the N cap. The frame is given by T cap and N cap. Two mutually orthogonal length 1 vectors. It's an orthonormal frame. Okay. How they behave with respect to time, their derivatives, that tells you how the frame moves. If I have that information, I should get back my curve. You see, it's very, very natural. And what happens is that here is where something amazing happens. This whole curve, if you want to make this mathematically precise, this whole thing can be written as a single matrix differential equation. Okay, that becomes the dynamic equation of a moving particle on the curve, and this curve becomes the unique solution of that dynamic differential equation, a matrix differential equation. And that differential equation, that differential equation is what is called the Frohn's-Serre equations. Okay, and the beautiful thing is that these Frohn's-Serre equations, if you want to get them, you have to understand where the sine curvature comes from, where the sine of the sine curvature comes from. Okay, so that is one motivation to understand the sine curvature. So let me write this. So basically what happens is you will get, see, just think about it for a moment. This T cap dot is what? It is a derivative of T cap. Okay, it's also a vector, but you see this T hat and N hat, they are two vectors. Mind you, I am only on a plane curve. You know, if I give you if I give you two linearly independent vectors, any vector can be broken down as a linear combination of any two linearly independent vectors. In this case, they are even not only linearly independent, they are unit length and orthogonal. Okay, so any vector on that plane can be broken down into t cap and n cap components. All right, so you should be able to break down t cap dot in terms of t cap and n cap. Similarly, you should be able to break down ns n cap dot also in terms of t cap and n cap. Okay, and therefore you are writing t cap dot and n cap dot in terms of linear combinations of t cap and n cap. That involves, of course, 2 by 2 matrix. Okay, if you write a single vector, you write it either as row vector or column vector. If you write two vectors, you will have two rows or two columns, so that's a matrix. So what do you get? You get the following thing. You will get t cap dot n cap dot ns cap dot is equal to, okay, so let me write it like this. This let me write it as a matrix like this. So I'll get ks minus ks 0 0 t cap ns cap. This is the equation. So in other words, this is the same as writing t cap dot is just ks ns cap and ns cap dot is equal to minus ks t cap. Okay, so you see that means t cap dot has only n component in the ns cap direction and ns cap dot has only component in the t cap direction. Okay, and this is the matrix you get, and this is a matrix differential equation. And the beautiful thing is that you see this is a simultaneous system of first order differential equations. And what is the curve? The curve which is given by gamma t is the solution. Okay, and by geometry, because this Q symmetric matrix is involved, okay, notice that this is Q symmetric matrix, it is equal to negative of its transpose. Okay, all the diagonal entries are 0. Okay, and because of this Q symmetric matrix, this curve is completely fixed up to rigid motion. Okay, and rigid motion will involve only translation and rotation. Okay, and what I want you to appreciate is that this ks, okay, the sign curvature comes here. You see, the sign curvature is so important. The sign of the curvature keeps track of the dynamics of the curve. The sign curvature gives rise to this matrix differential equation, for which the curve is the unique solution up to rigid motions. So you see, you have this very beautiful thing, and therefore, this t hat n hat is called the Frohnert-Serre frame. This is called the Frohnert-Serre frame. Okay, and these are two mutually orthonormal naturally defined vectors. Okay, and of course there is you can guess I am doing this for plane curves. It will also extend to space curves. There you will have 3 of them, and you will have a 3 by 3 matrix. You should expect that 3 by 3 matrix is also going to be skew symmetric. Okay, and it will have one more entry. Guess what it is? It's going to be the torsion. Because for a space curve, there is one more curvature, which is the second curvature, the torsion is going to come in. Okay, so that's a beautiful thing. You have this Frohnert-Serre frame, and these are called the Frohnert-Serre equations. Okay, and basically they are dynamical, matrix differential equations, a pair of linear differential equations whose solution is the curve, and the solution is unique. If you say I want a curve passing through a point with a fixed frame at that point, you will get only one curve. It is uniqueness. Basically, it becomes uniqueness of solutions of first order differential equations. Okay, so you see that this is such a beautiful interpretation. So we will derive these Frohnert-Serre equations. We will use for this Frohnert-Serre frame. Okay, and this is the beginning of the story. That this is the starting point of saying this fact that when you naively say that the curve is controlled by the curvature, okay, then what do you mean? Actually, the truth is the curve is not just simply controlled by its curvature, it is controlled by its signed curvature. Because once you give me the signed curvature, you can form this matrix, then solution of this matrix differential equation is your curve. That's it. That is a mathematical formulation. Okay, so that's what you have to appreciate. Okay, so all this is just the motivation as to why you have to dig into what this sine curvature is. Okay, so I'll give you one more motivation, which is another very deep thing, which goes all the way far away into the so-called one of the epic theorems of the topic, which is the Gauss-Bonnet theorem. Okay, so here is another motivation. So I'll just say the above tells us the importance of understanding the sine curvature. Okay, and of course the sine curvature and also the sine normal. Okay, mind you, sine normal is also involved anyway. All right, and I sometimes I put the cap, sometimes I don't put the cap, but I always put a cap to keep reminding you that it's unit vector. Okay, all right. So here is one more piece of motivation. So I think I wrote. So here is the other piece of motivation. So what is the other piece of motivation? So let me use a different color. Let us see. Okay. So this business of total curvature. See, yeah, it is a good question to ask why you don't have a notion of sine tangent. But the truth is that you see, this sine normal was defined because a unique normal was not defined. But a unique tangent is always defined. See, the moment you write the parameterization gamma of t, where t is a parameter, then gamma dot of t already gives you a vector direction. So that is the tangent direction is uniquely defined. The once you write the parameterization. Okay, what is not defined is the normal direction. In the normal direction, you have a normal line and two possible normal directions. You will have to make a uniform choice of normal. And so what we do is that since the tangent direction is properly defined, it's not done on a case by case basis. The tangent direction is always well defined. From that, you just rotate by 90 degrees anti-clockwise and say this is the sine normal. And once you do that, you see, you will have to introduce the sine curvature. But the problem is that only for the normal direction you don't have a well-defined direction to begin with, whereas for the tangent you have. So you don't need a sine tangent basically. I mean the sine is required only for the normal direction where you have to decide which direction you are going to take. But it has to be dependent on something that's already well defined, and what is already well defined is already the tangent direction. The tangent direction gets well defined the moment you write gamma t. The tangent direction is gamma dot t. So you rotate that by 90 degrees anti-clockwise once and for all and call for all cases call that as a sine normal. No, with the moment the moment you write gamma of t as a parameterization where t varies in an interval a to b, it is understood that t is increasing in that interval, and this increasing value of t already tells you how gamma t is going to be traversed. So you see the direction or the orientation as it is called on the curve, it's already given to you the moment you write out the parameterization. So the point is that the difference between just a geometry curve and a parameterization is not only that the parameterization gives you an analytic expression, it also tells you in what way you are traversing the curve as the parameter increases. So you see the direction is also given, that's called the orientation. So the point to note is that the tangent direction is always given unambiguously. Once you give me a parameterization, what is not given is a normal direction, and that's the reason why we want stick to a particular normal direction. We do this thing, we take the tangent direction, rotate it by anti-clockwise by 90 degrees, and for once and for all call it as the sine normal. Okay, and why it is called the sine normal is because it will interfere with the sign of the curvature when you try to write that vector equation. You understand? So that's the reason why you don't have a signed tangent, but you have a signed normal. Okay, so let me come to this other important thing, why you have to understand as to why you have to understand the sine curvature. So let's do a very simple calculation. Let's take the circle. Let's take a circle of radius r. Okay, and let's assume that you are traversing in the anti-clockwise direction. Okay, what is the curvature? The curvature the curvature k is 1 by r, that is constant. Okay, now what I am going to do, I am going to go once around the curve, this circle, and I am going to calculate the total curvature. what is the total curvature? The total curvature is I have to integrate over the circle, okay, which means I have to integrate over the arc length of the circle, okay, integrating along the circle is integrating along the arc length, okay. I have to integrate this function. So the total curvature will be integral over the circle of k ds, okay, and if you calculate it, this k is 1 by r, so integral over the circle, integral over the circle 1 by r ds, and I will simply, this integral over the circle, since s is the arc length, the limits will be, let us say I start at some point, if I start at some point s is equal to 0, I call it as s equal to 0, then if I go back once, if I go around once, I will get s is equal to 2 pi times r. So this will become 0 to 2 pi r, 0 to 2 pi r 1 by r ds, and see what you are going to get. You are going to get 2 pi. So 2 pi r by r is 2 pi. Okay. So you see what is happening. The total curvature is 2 pi. Okay. I am getting this. Of course, you know, if you are going to take sine curvature, what is going to happen is, if you integrate the sine curvature, if you are going in the anti-clockwise direction, you will get 2 pi. If you go in the clockwise direction, okay, then what will happen is you will get minus 2 pi. Okay. So you see what is happening. The total curvature is 2 pi, it's an angle. Okay. Now here comes the amazing thing. There is something called Hopf's Umlaufsatz, which says you take a simple smooth, you take a take a simple smooth closed curve. It may twist and turn whichever way you want, it may want. You go around once, okay. If you take the sine curvature, depending on the way you are going around, anti-clockwise or clockwise, you will always get only plus 2 pi or minus 2 pi. That is the Hopf's Umlaufsatz. And basically it will seem that this is such a silly, you know, result, this should be an obvious result. But believe it or not, the proof is quite involved. It involves enough amount of topology, homotopy, manifold theory, analysis. If you want complex analysis, the proof is really not, you know, so easily, you know, describable. Okay, but the statement is very, very simple. So what I want to say is that this Hopf's Umlaufsatz also can be made sense of if you understand sine curvature. And the Hopf's Umlaufsatz is the simplest case of the Gauss-Bonnet theorem, okay, and whose motto or whose paradigm is total curvature is always an angle. It's actually n times 2 pi, and that n is a topological quantity. It has got nothing to do with differential geometry, okay. So it's something very amazing, and this is the simplest case. And to understand this also, for curves you need the sine curvature. So that's another motivation for understanding sine curvature. Okay. So I will stop here. We will continue in the next lecture. All right.